So what really prompted this is, and I'm not sure how aware of, what everybody, if we keep up to date on what's going on at the K-12 level, but I'm sure you've heard of Common Core and this whole idea behind, adopting these standards that are national, that everybody's kind of learning the same thing. Well, if you get onto any social media site, there's all these examples of how Common Core is ruining mathematics. And the public perception is that Common Core is a way to teach mathematics. Most people don't understand it's just a set of standards. This is what students should learn in first grade. This is what students should learn in second grade. And so there's some of these examples of these different ways that educators have been using to teach things like addition, subtraction, multiplication, and division that we're going to talk about. And we'll talk about why they're using some of them and why the reason is to ultimately get to the algorithms that we're used to, but they're making these processes a little more transparent for students. Well, the general public sees some of this stuff and they think this is how all students are doing math now, or they see it and it looks so different. And they're like, why are they ruining math? Why can't we just keep math how it was? Why are they changing it? Well, really, it's the same idea. We're just changing how students are arriving at the answer to appeal to different aspects of their learning. So, like I was saying, what is this new math they're teaching? I hear this all the time, this new math. It's not. It's not new. But what they're trying to do, what some of these processes that we're going to look at, these algorithms, are we're emphasizing the process and making it more transparent, especially when you're talking about things like borrowing and carrying, when you're adding and subtracting. Okay? We expect students just to look at the number in the second place and know that it means 20 instead of 10 when we're doing subtraction. Well, these processes are going to make that more transparent for students. We don't expect them to solve problems this way forever, but until they understand what they're doing, it helps them to see that better. Some of these methods you'll see apply to the visual aspect of learning. Okay. What you'll see, and you'll probably think this as I'm showing you some of these examples, is that sometimes these take a little bit longer than the algorithms that we're used to. Most of these are less efficient. But like I said, we don't expect students to do it this way forever. We ultimately want to get them to the algorithms that we use, which are pretty streamlined. But what we're trying to do is get the understanding there before they start using those very streamlined algorithms. And then we're attempting to make those abstract ideas, like I said, about borrowing and carrying more concrete. They can actually see how they're borrowing 10 instead of just adding a 1 on. And then I always hear, well, why change it? Why not just use what works? Works for me. I know how to do long division. I know how to multiply double-digit numbers. Why can't they just learn that? Well, for some students, those standard algorithms initially don't work. They just follow the algorithm, and they don't understand what they're doing. And so when they make a mistake, they don't understand what the mistake was or why they got the wrong answer. They just think, oh, I'm not good at math, I can't do this, because they don't understand how it's working. So these new algorithms and these processes that I'm going to show you are designed to help students to understand the process rather than just plugging in some numbers and following some steps that somebody told them to do. So they're viewing math as they're getting an idea of why are we doing this, what are we doing, versus, well, my teacher said first I do this and then I do this and then I get my answer, without any understanding of what they're doing. And like I was saying, eventually, and you'll see this with division, the idea is that students like to get things done quickly. So eventually they'll use these algorithms and they'll start getting more proficient at it, and they'll try to get to the answer faster, which will eventually, for long division, get them to the algorithm that we're used to for long division, because they don't want to, waste all this time on a problem. They want to get it done quickly, and so the better they get at it, the quicker they can arrive at the answer. So we're going to look at a couple of different operations. There are a lot of different ways to represent multiplication. So we're going to look at, and these names are interchangeable just depending on who uses them and where they use them, but we're going to talk about the array method, the bow tie method, partial product, lattice, and then the box method, which is similar to some of the other methods, but we normally use this when we're working with polynomials. And so this box method, when we get to it, is going to be a good example of making things more visual for students. For division, we're going to look at what's called the Hangman Method, and then carrying. And then subtraction with, oh, that's supposed to say regrouping. Oh my gosh. At least it wasn't a comma mistake. Regrouping in place value. And then this is the one that I've seen so much on social media that's ruining math. Starting out teaching subtraction is the reverse of addition. I see so many people who see this and they think this is how we're teaching subtraction now. And we're not teaching, regular subtraction this way. This is a starting point to get students to understand that subtraction is reverse addition. All right, so I'm going to do some of these examples on the whiteboard for you. And we're going to start with multiplication because there's a lot of different methods that are used. So we're going to start with the array method. And so this one emphasizes the idea of place value. And it also this marker is not going to work for me. It also makes things more visual. So I'm going to show you two ways. One for a student who is less proficient at multiplication, and then the way that we could do the same problem for a student who's maybe a little more proficient with multiplication. So we're going to look at the problem 24 times 36. So with the array method, so for a student who isn't very good at multiplication and they don't maybe know anything past their tens, what we can do is we can break each number down. So I'm going to break 24 down into 10 plus 10 plus 4. Because I know how to multiply with tens and I know how to multiply with 4. And then I'm going to break 36 down into 10 plus 10 plus 10 plus 6. So the idea here is I don't really know any multiplication past my tens. That's when it gets tricky for me. And so we're going to make this into a nice little grid here. Separating each number. And then we're just going to multiply. So for all of these, 10 times 10 is a really easy multiplication for students. And then we'll do this 10 times 10. And then 10 times 4 gives me 40. And then the same thing here. 10 times 10 is 100. We get 100, and we get 40. Same thing here, 100, 100, and 40. And then we get 60, 60, and 24. So I've multiplied each of these individual parts, and then I'm going to get a total, because all of this was addition. So looking at this, I can see that I have 6 100s, so I know that that's 600. And then I have 3 40s, so I know that's 120. Or if they didn't know that, they could just start adding 40 plus 40 plus 40. And then I have 2 60s, which is also 120, and then I have the 24. So this gives me 864. So I know that 24 times 36 is 864. So from this point, once students got better understanding multiplication, we could make this less complex. So instead of breaking it apart into all these tens, we could just do 20 plus 4 times 30 plus 6. So then we could do 20 times 30, which is 600. 30 times 4 is 120. Then 20 times 6 is 120. And 6 times 4 gives us 24. And then we could add those values just like we did in the last one. And that gives us 864 as well. So that's what's called the array method. And this is emphasizing we initially start out, like I said, because students aren't very good at their multiplication facts, so they're working with really easy numbers. And then here, we're also emphasizing that place value. So we're, instead of just looking at this as a 2, like we might during normal multiplication, we know that it's 20. So similar to this, and this the next example is going to be very much like this one, but it's a little more, I'm just going to say gimmicky, a way to get students to remember. This is what's called the bow tie method. And we'll look at the same problem here so you can see how it's similar. And so again, with this method, what we're going to do is we're going to break this apart into the 2 different place values. So we're going to have 20 plus 4, and then 30 plus 6. And we're matching up the place values. So I'm matching up the 20, and I'm at the 10s, and I'm matching up the 1s here. And so the way that they teach students to remember everything that you've multiplied, kind of like what we do when we tell our students to FOIL, okay? It's kind of a gimmick to help students remember to distribute correctly. This is going to end up looking like a bow tie. So I'm going to start multiplying down first. So 20 times 30 gives me 600. And I'm going to multiply down over here. So 4 times 6 is 24. And then to make this look like a bow tie, I'm going to multiply across. So 20 times 6 is 120. And then I'm going to multiply across this way. And so that's going to give me 120 as well. And then just like we did in the last one, now I'm going to add all of these together. So the 600, the 2 120s, and the 24. And that's 864. So it's similar to this, but instead of using a box, we're just making a bow tie. Now, the problem with this one versus the array method is this will only work for double-digit numbers, and you have to have 2 double-digit numbers, unless students know to put a 0 in front to teach them that there's nothing in the tens place. But if you had 3, then you couldn't make the bow tie. So this only works with double-digit multiplication. Okay, next one is what we call partial product. And so this one would be where we're moving students away from the array method. We're still using that same idea of emphasizing place value, but now we're getting more toward the standard algorithm. So again, we'll look at 24 times 36. And so students would start by setting this problem up just like we would when we were multiplying. So we would have 24 times 36. But instead what they're going to do is they're going to do each multiplication separately and then add them all together. So students would start by saying, okay, 6 times 4 is the first thing we would do, is 24. And then I have to multiply the 6 by the 20. So 6 by 20 gives me 120. Now I'm going to do, this is now 30 times 4 is 120. And then 30 times 20 is 600. And so what this does is students don't have where they have to carry numbers over into the next column and then remember to multiply and then add on what they carried. So they're just looking at each individual piece here. And then they would total this up and again get 864. So we're getting closer to our standard algorithm, but they're still using all of these sums instead of just the 2 that we would end up with. They also don't have to remember to add the 0 when they move over a place value. All right, lattice method is one that I see a lot of students end up using. And so for this one, we'll look at 89 times 45. So we're going to start out, and it's going to look similar to the array method where we're using boxes. So I'm going to have 89 and 45. And then I'm going to separate these. And then what we do with the lattice method is each box is separated on a diagonal. And so from there, we multiply each separate number. So I'm going to do 4 times 8, which is 32. And so if something's in the tens columns, it's going to go on top, and then the ones column goes on the bottom. So I would write it like this, 32. And then 9 times 4 is 36. And then 8 times 5 is 40. And 9 times 5 is 45. Okay. And then what we do to get our answer to this is we add on a diagonal. So this first diagonal right here will give me 5. That's my first digit. Then I have 6 plus 4 plus 0, which is 10. So I write the 0, and then I carry the 1 over to the next diagonal. And so over here, this gives me 10 as well. So I write the 0, and I carry the 1 to the next diagonal up. And then I add the 3 and the 1 to give me the result, which is 4,005. Then one nice thing that a lot of students really like about the lattice method is that there's a little trick that they can use for decimals. Instead of having to remember, okay, I had 1 decimal place in the first number that I used, and I had 2 in the other, so I need 3. So we'll look at 17.2 times 3.6. So we're going to set this up the same way. We'll do the 17.2 on top, and then the 3.6 we'll do down here. And then I'm going to make sure I'm going to do this in a different color so you guys can see it better. I'm going to line my decimal up with the line that is in between the 2 numbers where the decimal is. Okay, so it was between the 3 and the 6, so I'm going to line my decimal up with this line. And then it was between the 7 and 2, I'm going to line those up. And so then we're going to go through again and separate all these. Cut each box in half, and then we're going to do the same thing. Here I have 3 times 1, so I would write this as 0, 3, because there's nothing in the 10 spot. And then 6 times 1 is 0, 6. 3 times 7 is 21. 6 times 7 is 42. 3 times 2 would be 0, 6, and then 6 times 2 is 12. And so I'm going to add on a diagonal just like I did in the last one. But how I figure out where my decimal goes is I'm just going to find the intersection between the two, where these 2 decimals would meet, which is right here. And so my decimal is just going to follow that line, and it's just going to stay right there. So when I add my diagonals right here, this just gives me 2. This diagonal right here gives me 9. And then this diagonal is going to go on the other side of my decimal, so that gives me 11. Carry the 1, and that's going to give me 6. So this is 61.92. And so again, the idea here is that students don't have to remember the rule for multiplication. They just have to line up where the decimal places go. Before I erase, are there any questions about any of these? Yeah?
So you have 1 decimal place and 1 decimal place where no matter how many, like if it was 1.72 times 3.6, it would still be the same, you would just move it.
Right. Any other questions?
I learned this, I took a history math class, and I never saw it used in a modern setting until I was teaching 097, maybe 10 or 15 years ago, and I saw students use it. When did this become common? Because it's fairly common.
Yeah, it is. And you know,
When
honestly,
did it become common in math education in this country?
I think a lot of it too is regional, and you know how there's those trends that sweep through education. When I first started teaching and I'd have students come in from pre-algebra, I never saw this. About 2 or 3 years into it, so about 7 years ago, I started seeing this all the time. And so I think it just kind of depends on, you know, what, if somebody goes to a conference and they bring it back and everybody starts teaching it that way, or one teacher does it and another teacher starts doing it and it catches on. But yeah, I didn't see it for quite a while, and now with like my 096 kids, I only see like 2 or 3 students do it, and the rest of them will be doing it the other way, but then I'll have a class where I see 5 or 6 or 7 of them doing it that way. And again, this one is just more for the visual learners. This helps make it more visual for them. I think that the problem with this one versus the other ones is, again, they're just following a process and they don't really understand, okay, why do I add on a diagonal? They don't get that part. So I think the other ones make sense in terms of helping students to better understand the process and to understand that this is 20 times 6 and this is 20 times 30. Where this one, you know, they're just following a process, but it looks nicer and it's easier to, you know, do the multiplication that way because we don't have to remember to add a 0 when we go down to the next line. So similar to some of these, I see a lot of students doing this with polynomials, and this is what sometimes is called the box method, because it's the box. And so we'll just start with a binomial times a binomial. So we'll look at 2x minus 5 times 3x plus 7. So what students will do is they'll take and they'll separate the terms. So we'll have 2x and minus 5. And then on the top we'll have 3x and then plus 7. And so just like we've done in the other ones, my box is really uneven. There we go. Like we've done in the other ones, just separate each term, and then they'll go through and multiply each term. So 2x times 3x gives us 6x squared. 3x times a negative 5 gives us a negative 15x. 2x times 7 is 14. And then negative 5 times 7 is negative 35. Oop, I forgot the x. So the one nice thing about this, because it's just like foiling, it's just like distributing. But what's going to happen, and I'll do a binomial times a trinomial next, is what's going to happen is always on our diagonal, our like terms are going to end up always ending up on a diagonal there. So just like with the lattice method, we can say, okay, we have a negative 35, and then on this diagonal, we're going to have a negative x or a negative 1x if they want to write the 1, and then the 6x squared. And so this doesn't just work, unlike the FOIL process when we tell students to FOIL, they can't use that with anything other than a binomial and a binomial. So if they wanted to do, let's say, 3x plus 4 times 2x squared minus 5x plus 1, we could also use the box method for this. So again, separating these out into 3x and plus 4, so we remember that it's positive. And then 2x squared minus 5x and plus 1. And then go through and multiply each intersection together. So this would give us 6x cubed. This would give us negative 15x squared. and this would give us 3x. This would give us 8x squared minus 20x, and then 4. And then once again, on our diagonals are going to be our like terms. So I have the positive 4. 3 and then negative 20 would give you a negative 17x. Then we could combine our x squareds because they line up on a diagonal, so negative 7x squared. And then I have the 6x cubed. So that's how we're kind of applying those earlier methods of just basic multiplication and using it. And really, this is, like I said, it's the same as the distributive process, but it makes things a lot more visual for students. It helps them separate it out instead of, you know, trying to remember, okay, did I go to that one next? All right, so now we'll look at division. And the first one I'm going to show you is, I've mostly heard it called the Hangman Method because it looks like, when you set it up, it looks like you're going to play hangman. And so we'll look at 356 divided by 24. So the idea behind this approach is, first of all, for students who aren't very good at their multiplication tables. They don't know, you know, how many times can one number go into another number. And it kind of takes the stress off of, okay, I have to find exactly how many times, you know, 24 can go into 356 the first time. So what they're going to do is they're going to set this up just like we normally would. But then we're going to kind of make it look like hangman. Okay? And so a student would look at this and they're going to say, okay, I don't know how many times 24 can go into 356, but I know if I multiply 24 by 10, that gives me 240, because I just add the 0 on. So I'm going to multiply this by 10, and that's going to give me 240. And so when I subtract those, I have 116. Okay, I don't know how many times 24 goes into 116, but I'm guessing, I know it's more than 1, so I'll just say 2. I'll say 2 and I'll see what happens. So I'm going to multiply 24 by 2, and that's going to give me 48. And then we'll just subtract those. And that gives me 68. Okay, I don't know exactly how many times, but you know, I did 2 last time and that was easy, so I'll try 2 again. And so that gives me 24. Oh God, yeah, 48, thank you. And so I have 20 left. And that's smaller, so I can't divide it any further. So what I'm going to do is all these numbers that I used, I'm just going to add those together. And so that gives me 14 with a remainder of 20. Okay. And so like I said, this is really good for students who don't know, they're not really comfortable with their multiplication tables. A student could make this really simple, but for us really complex, and they could just say, okay, it's going to go in one time, and they could just keep subtracting 24 every time. But we know that students don't like anything that takes a really long time. So eventually they'll start making better guesses, and they're going to try to get this done as quickly as they can, which is ultimately going to get us closer to the division algorithm that we're used to. Okay? A lot of people I've talked to who use this say the students have to guess how long they're going to have to make this. How many guesses is it going to take me to get to the answer? And they'll have students who'll say, well, I think I can get it in 3. Well, the next student says, I'm going to get it in 2 then. And so then it becomes kind of like a game. But as I was saying, it kind of takes that pressure off of getting it exactly right the first time, and then having to do the more difficult multiplication, having to work multiplication off on the side, because what they're doing is they're choosing things that are easy that they can do mentally, and things that they know. I know if I multiply by 10, I can just add a 0 on at the end. So the other one is what's commonly referred to as carrying. And so we're going to look at 697 divided by 5. So what you'll notice about this one is it's not very different than what we do for long division. The only difference is how it looks when they're writing the problem out. And we're using kind of something similar to if a student was comfortable with carrying and borrowing with addition and subtraction, this looks similar to them than what we normally do with long division. So we would set it up the same way. 5 into 697. And so what we're not doing here is having everything below this. We're not writing things down. So we're just saying, okay, how many times can 5 go into 6? Well, it can go in once. And so then I would have 1 left over. So I'm just going to carry it over to the next column. Now I see that this is now in 19. So how many times can 5 go into 19? Well, it can go in 3 times, and that would leave me with 4. And then how many times can 5 go into 47? And that would be 9. And then we have a remainder of 2. So it's very similar to long division, except we don't have, it looks a lot cleaner and faster and shorter for students. They're not doing the multiplication and then subtracting. Now this is going to be a lot harder for students if this were a number, if this were a double-digit number. Okay, this works really well with single-digit numbers, but once you start getting into double-digit numbers, then the standard division, long division algorithm works better because they have to do the multiplication. But when they start out and the products aren't that big and they have a single-digit divisor, then this just looks more like what they're used to in terms of addition and subtraction and the borrowing and the carrying. Questions on either of the division ones? Mm-hmm.
You might explain that one again.
Mm-mm. Not at all. And actually, let's do a different problem. Let's say we're going to do 792 divided by 4. So we're going to set it up just like we normally would. And we're going to say, okay, how many times can 7 go into 4? It can go in once. And that would leave me with 3. So I'm going to carry the 3 over. So now I look at this as a 39. How many times can 4 go into 39? And that would go in 9 times. And so 9 times 4 is 36. That would leave me with 3. So I carry that 3 over to the next column. And then I would look at this as 32. How many times can 4 go into 32? That goes in 8 times. So my answer is 198.
I get it now.
Any other questions on the division before we look at subtraction? All right. And the one I'm going to show you with subtraction also works for addition. And it's similar to the array method for multiplication. And so we're going to start with double-digit subtraction, and then we'll do where we have 3 digits. So this is just subtraction with regrouping. So let's say students were given the problem 52 minus 24. What students are asked to do is to break these apart into their place values, just like we did with the multiplication. So 52 is 50 plus 2 minus 24 is 20 plus 4. So I'm trying to do this subtraction, and I know that I can't do 2 minus 4, so I have to borrow from the next group over. And so now looking at this, I see that this is 50, and I have to borrow from the tens, so this is going to become 40, and I'm going to add the 10 over to this column, which gives me 12. Then we can do 12 minus 4, which is 8. And then we can do 40 minus 20, which is 20. So my answer, when I add my tens and my ones, is 28. So the idea, again, behind this one is we're making that borrowing more transparent for them. They're seeing that it's actually 50 and that we're taking 10 from the 50s and moving it over to the ones place. And so you can do the same thing . Let's look at 528 minus 246. We can do the same thing with as many digits as we want, but we can do the same thing with 3 digits. So I would break this apart into 500 plus 20 plus 8. And then we're going to subtract 200 plus 40 plus 6. So here I can do the 8 minus 6, which gives me 2. Now here I can't do 20 minus 40, so I have to borrow from the next column, which I see is the hundreds. So I'm going to take 100 from here, which is going to make this 400, and I'm going to add the 100 over here, so that gives me 120. So 120 minus 40 is 80. And if students didn't know that, if they weren't quite proficient, they could do the same idea. They could take this problem and break it apart, but usually once they get to 3-digit subtraction, they're better at doing 12 minus 40 is 80. And then 400 minus 200 is 200, and then they're just going to add all those together to get their answer of 282. Questions on that one? And again, the emphasis here is to line up the place values. So if this had been 3 digits and this had been 2 digits, they would have just not had anything in the hundreds column right there. So the last one is the one I was telling you about that has everybody all upset. Subtraction as reverse addition. So we're going to look at 32 minus 15. And so what we would say to students is, I'm starting at 15 and I want to know, how do I get to 32? And students might not be comfortable yet with subtraction. And so this is another place where, just like with the hangman idea of division, they can kind of use their estimation skills, or they can just use smaller numbers that they're comfortable with. So I'm going to start with 15, and I want to get to 32. Okay, well, I know if I add 5, that's going to get me to 20. So now I'm at 20, and I know that to get to 30, I can just add 10. So now I'm at 30. Well, to get from 30 to 32 is really easy. I just add 2. So now I'm to the answer I want, and so everything I added on is my answer. And so, like I was saying, people think that this is how students are learning to subtract, rather than how we would, okay, we're just going to borrow from here, change this to a 2, and do 2 minus 1. And that's not the case. This is starting to implement the idea that subtraction is the opposite of addition, and getting them to see how we can work backwards. But we're not going to have, 20 years down the road, we're not going to have everybody who's 30 not knowing how to subtract and just trying to add to get back to the answer. Okay, it's a basic building block for eventually getting to here, where we have to start talking about place value and borrowing and carrying. Questions on that one? I had so many people too who didn't understand what was happening. I saw this on social media and they were like, I don't understand where they got that answer. And it was like, well, you've been using this algorithm that you probably don't actually really understand, and so of course this doesn't make any sense to you.
Have you seen anybody teach that? I'm just wondering. My questioning is, it seems to me that sometimes part of the issue is that you have people teaching things that they don't really get.
Right.
And so it becomes this different process, and they're not making those connections like you said, that this should be building somewhere, and I feel like sometimes they don't build.
Yeah, I haven't.
Here's this and here's this, and they're not helping them put pictures of it.
I haven't gone into a classroom and actually watched somebody teach it, but I know that in some places they are starting out with this. But I think you're right, and I think that's the problem, is that somebody's showing them a process that they don't really understand themselves, and so it's getting the idea behind it, those connections aren't being made.
I really like that. I've never seen it before.
I've-
It reminds me immediately of just making change.
Yeah.
You buy something for $2.92, you pay with a $5 bill, and in the old days, it's got to be of a certain age to appreciate this.
Yeah, you work backwards.
Here's 8 cents, and then here's 2 $1 bills.
Yeah.
You add the 8 to get to 3, and then there's 2 more. I think that's really nice. I
Yeah.
don't know what level I would. Those of you, I'm not taught 095 here. Those of you who teach 095 here, 096, do you do stuff like that in here? I really like that.
Here's the only, I think this is all wonderful, and it's really cool. The only thing is, it seems like in my experience in 095, is that you teach a process,
Yeah.
and then you practice that process. Whereas this is, like I said, this is really neat, but as far as, they learn a process, well, am I gonna learn this process, or am I gonna learn this one, or this one?
Right.
And that seems to be,
And the idea, though, is that some of these are just starting points. Like, I wouldn't expect my students to subtract this way forever. I might start showing them this so that they really understand that when they're doing 52 minus 24 and they're borrowing from the 5, they're not borrowing 1, they're borrowing 10. So all of these are really starting points. Like I was saying with the division, the idea is to eventually get them more efficient at it and get them to that standard algorithm. But what these are really doing is emphasizing understanding versus, well, my teacher said that I see how many times this goes in, I write the number up there, and then I multiply, and then I subtract, and they don't know why they're doing it.
What I found is, as with kids that just finished learning some of these methods, which I was initially horrified by.
Yeah.
The Hangman method, they run into problems when it no longer works.
Yeah.
When they have numbers where they have remainders and they need decimal points, and my kids made that transition.
Yeah.
And I was sure they weren't going to be able to.
Right. And like I was saying, and I think that's part of the problem. A lot of people see it and it's not what they're used to. And like the Hangman and even this is less efficient than what we do. We're used to finding the most efficient method and let's do it that way. But so many people use that most efficient method and they have no idea why they're doing it. So here, what we're trying to do is build the understanding and then get them to those very efficient algorithms that everybody else uses, so that you can look at and know it's long division instead of this new math that everybody's teaching.
In 097, we're trying to teach all of elementary school math in one little semester, and so you don't have time to go through the processes like,
Yeah.
if I'm teaching,
right.
elementary school, I have a whole year to do addition.
Right.
And spend all that time, but it's hard to implement this stuff, at least I found. I was trying to go into.
Yeah.
I just see
and do those things.
teaching the old the algorithm like we normally do, and then introducing this, and having students just, I do what?
Yeah. Although
What?
try teaching them the Hangman for division to get them started.
The second one is really sweet.
Yeah.
Because the thing in long division sometimes is you get all those numbers underneath.
And
there.
they don't want to write a lot.
And they don't even, and the way you did there was bam, 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 that was sweet.
Yeah, they like things that are quick and fast.
It's only with a one-digit divisor for the most part.
It's better.
It gets more complicated, and then that's when they'd have to be doing division off to the side, so, using the standard one. But, I agree, and you can't teach all of these. You can't say, okay, well, here's one. I mean, students get too confused, but I think they're good to have if you have a student who's really struggling, and you say, okay, you're not getting it this way. Let me show you this way that makes it, maybe a little more work, but you understand it better. But wouldn't it be nice if a lot of students understood this by the time they got to us? You know what I mean? If they started out learning this in elementary school before they learned what we normally teach, so that it made sense to them. Any other questions, comments?
The way you did the division, where they do the subtraction stuff in their head, is the way some countries teach it, and especially Hispanic countries.
Yeah.
And so you might see students who are appalled that they're actually, I should write down the subtraction step. No, I have to do that in my head kind of issue.
Yeah. And, our students, like I was saying, they don't want to write a lot. They like to try to do stuff in their head as much as possible, which is where that one works really nice. It works best with a single-digit divisor, but, it's neater. There's less mess. It's quick and efficient. Any other questions? And like I was saying for addition, we can use this same idea, breaking it apart. If a student is having problems understanding carrying, if we change this and we got something that was bigger than 10, then they know that they just leave the 1 and they add the entire 10. Instead of just adding the 1 onto the next column, they add the entire 10. Well, that's all I have.
When are you going to do something like this with fractions?
Fractions is a whole new ballgame. And no, I have been looking into some fraction stuff, and I keep finding all these things that say, fractions, you're teaching them wrong. And so I'm going to do some research into these things that are being put out there. What are we doing? What are we all doing wrong here? Here is a simple and easy method to get your students to understand fractions the first time. So I'm working on it. I'll let you know.
That's 1, 9, 5, 6, 7, that's their favorite stuff.
Oh, 110, they love fractions.
Well, what did we hear, those of us who were in that meeting where the gentleman from Alex discussed issues that calculus students had in their preparation for calculus?
Mhm.
Their biggest problem? Fractions.
I tell my
Calculus students.
I tell my 095, 096 students that right now. When I taught calculus, the difference between an A student and a C student, the A student knew how to work with fractions. And that's really what it was. When they had to, decrease the exponent and they had 1 half minus 1, they were like, what do I do? Well, you subtract. And that's what happened. And they didn't know how to work with the fractions.
Now all getting depressed.
I know.
Thank you very much, Eric.
Thank you.